Yes. So we have observed that IV characteristics of the MOSFET. Across the IV characteristics, we have verified the voltage variation of the gate terminal and corresponding response of the MOSFET. In the similar fashion, the variation of the VGS, VDS and the corresponding response across the MOSFET. But now in the third case, what I am trying to do is, I will be keeping the gate voltage and drain voltage as it is. I am now concentrating on the second gate, we call it as a body terminal, and the variation of the body terminal voltage, how the response we can observe across the MOSFET. We will be verifying that through the concept called body effect. So now let me bring one scenario. What we know is the MOSFET is a voltage control current device. As the voltage across the gate terminal VGS, it changes, the current across the drain terminal definitely has to be controlled. So as we know that current equation of the drain terminal is ID is equal to of mu COX W by L times of VGS minus VTH whole square. So as this formula says, the voltage across the gate terminal, if it is increased, the current has to be increased. If the voltage across the gate terminal reduced, the current also reduced. Means the current which is flowing across the channel of the MOSFET directly depends upon the gate voltage. That is how we call it as a voltage control current device. So now if the device is connected with some amount of the current is flowing, the same ID current which is flowing across this one, if it is around like 72 microamperes, which is connected to the load over here. So this is my LED, this is my LED, yes, this is my LED, where the brightness of the LED with the current flow, it is depending upon the current flow. If the more current is flowing, that the brightness will be more. Because of the 62 microamperes current, the brightness is not maximum. So the brightness is not maximum. So what I need is the brightness of the LED should be maximum. For that, if I need it around like 68 microamperes, 68 microamperes, the current over here it should be 68 microamperes. If I need the current across the transistor is 68 microamperes, 68 microamperes. So only the chance is I have to increase the gate voltage. So if that gate voltage is increased, right, automatically the current across this one is also increased. But the problem over here it is the circuit over here it is given with the biased voltage of gate with through the ladder network over here. It is VCC, there is a R1 network, there is a R2 network. If this biasing circuit, if it is fixed, the voltage which I have provided with that whatever the current I am able to get it, it is fixed. Now the gate voltage across the gate terminal cannot be changed. So the device only can provide the 62 microamperes. The current over here it cannot be changed. Now we have to think, is there any other alternative where across the MOSFET where I wanted to increase the current across it is around 68 micro. So now my solution is, as we know the gate terminal, as we know the body terminal, this is my body terminal which is called as second gate. It means where across the body terminal I can give that external voltage where it was like grounded as of now. Now I remove the ground, I give 0.1 over here. Now I will give 0.2 over here. Like that, if I increase the voltage across the body terminal also, I can observe that the current flow can be increased. So now that the flow of the current it depending upon the body terminal, based on this formula I can justify. As we know the threshold voltage of the transistor is nothing but a VT naught plus gamma times of 25 plus VSB minus root over 25. So where VSB is nothing but the voltage between the source terminal and body terminal. So what happening is the source terminal and body terminal where I increase the voltage across the body terminal, so that what happening is, So the VSP is nothing but a Vs minus VB, let us suppose. Vs minus VB, let us suppose. So now let us observe that the internal resistance of the LED is 0. So that this is like the drop across this one is 0. So that source terminal is connected to the ground. And the body terminal potential I am trying to increase. Means the voltage over here it is increased. The voltage across this one is increased. Means this total term is becoming no more negative. Means this term is becoming more negative. This overall term is also becoming more negative. So that the threshold voltage of the transistor initially around 100 milli. So now what happening, it is becoming 90 milli and 80 milli and 70 milli and 60 milli. So like that the threshold voltage of the transistor is reduced as body voltage over here, it's 0, 0.1 and 0.2, 0.3, 0.4. As the body voltage increases, threshold voltage is reduced. So let me make it note. So the threshold voltage of the threshold voltage of the transistor MOSFET reduced with the increasing body voltage. So now what happening is, we have to observe that the threshold voltage of the transistor is reduced with the increasing the body effect through the simulation across the Tanner tools now. So now coming to the Tanner tools, this is what SC did. As of now we have observed that characteristics with this schematic. Now what I do is, I'll just remove the VSB equal to 0. Now I'll make the body terminal which is connected to the external source. So the body terminal which I keep it like this, and I will be giving a notation of that node terminal over here with the label body, and after that what I do is, I'll just generate a tSpice code once again. So with that the code will be generated like this, and whatever the DC analysis and whatever that comments, that how I give it, how that model files included, that's what we have already verified in the last session. That's why like I'm not going to discuss in again. So this is how model file is included, and now this is the one more step, like the body voltage which I am trying to give it as a DC voltage of 1 volt. So now I am trying to do the simulation, the DC linear source, the body voltage. What I am trying to do is, I am trying to increase from 0 to 0.5 with the step size is around 0.1. And now I will be verifying the drain current, and also I need the threshold voltage, because like I have to verify the threshold voltage of the transistor has to be reduced as like body voltage increases. 0 to 0.5, if I increase 0 to 0.5 increase the body voltage, if I increase, what I need to do is, I have to verify the current across the transistor. So now, and also the threshold voltage of the transistor. So now go with the output and the DC result. So where I have to put it as a expression. What expression? I wanted to calculate the threshold voltage of the transistor VTH. That is the expression for calculating the threshold voltage VTH of which transistor? The transistor which I have a notation MN MOS underscore 1, that I'll keep it and I'll add it, and I insert command over there. So with this command, the particular tool is able to give the value of VTH for the particular transistor. So now I will do the simulation. Now the simulation says simulation says as the body voltage increases, the threshold voltage of the MOS transistor, which is around like 100, right, which is around 100, it is reduced. Yes, so that's what like we observed through the equation. The threshold voltage of the transistor is reduced as the body voltage increases. So that's what we got theoretically and practically through the simulation also. And now as the body voltage increases, what happening is the drain current, which is around like 62 micro, so it is increased, right, it is increased. So now what happening, 62 micro, which is the flow of the current across the LED, now it is increased, so that whatever the brightness we are expecting, it can be achieved. As like you can increase the control across the gate terminal, I can increase the current flow. If it is not possible, I could increase the flow of the current through the body terminal also. By increasing the body terminal potential, what happening is, here I have the option over there indirectly, that VGS if I increase, ID will be increased. If the VGS I couldn't increase, what I am trying to do is I increase the body effect. With the body effect, what happening, the threshold voltage of the transistor is reduced, so that the overall term is increased indirectly. So the body voltage with which the threshold voltage is getting affected, because of the threshold voltage the current is affected, like I can increase the current flow. As the gate voltage increases or the body voltage increases, in both ways I can increase the current flow across the transistor. So I can say that the body terminal is the I can say that the body terminal is the I can say that the body terminal is the second gate for the transistor, so that I can increase the gate voltage or increase the body voltage to have the more conductivity across the channel.